This is the next video in the chapter on advanced theories of bonding. We just talked about the features of good orbital overlap, which are distance, orientation, and energy. We talked about distance first, so we'll talk about orientation next. So orbital orientation means which way the orbital is pointing, or in this case, which orbital you choose to do the overlapping. So remember that we like to draw a line like this, or sometimes you'll see it drawn like this. That refers to the internuclear axis. Which is just a fancy way of saying it is the line that you use to connect the center of the two nuclei. And so because we draw the line that represents a bond in between the two nuclei, we might have reached the conclusion that we need the electrons to live in this area, right? We draw this bond to represent two electrons that circulate around both of the atoms, both of the nuclei, but most of the time we need them to be in that space in between them. And so when we're choosing an orbital and an orientation, we want to choose one where the electron density is in that space between the atoms. So we want the electron density to be here in between the nuclei for a bond to happen. So let's think about the atomic orbitals that we know. We'll draw them on the left atom. So we know about the s orbital. And then we have three orientations of p orbitals, px, py, and pz. And so if we think about how well each of these different shapes overlaps with this internuclear axis, we can see that the s orbital is just awesome because it covers a large portion of that axis. There we go. The px orbital, also an awesome choice. Has a lot of overlap with that axis. And the py and pz orbitals, not so good. There is actually zero overlap with that axis. There is a node down the middle of the orbital on the line of that axis. So those two orbitals are not as great of choices to form a bond with. In particular, our favorite orbital is an s orbital because of their spherical shape. S orbitals have the best overlap in any direction because they're perfectly spherical. They have equal electron density in every direction due to their spherical shape. So no matter where that other bonding atom is, to the left, to the right, above, below, behind, in front, it's always going to have a good overlap with an s orbital. So if we need to choose an orbital, s orbital is always our first choice. So we sort of roughly decided which of these was good or bad, but let's dive a little deeper. Let's talk about what kind of overlaps are strong, what kind of overlaps are weak, and what kind of overlaps aren't actually overlaps at all. We're going to make a table here. Okay, so we have names for these kinds of bonds, and we used Greek letters because chemistry, Greek letters. So if there's a strong overlap between two orbitals, we call this a sigma bond. Sigma looks a little bit like a 6 on its side. If there is a weak overlap, this is called a pi bond. That's a capital letter pi. And if there's no overlap, then it is not a bond. You need to have orbital overlap in this model to have a bond form. So let's talk a little bit more about each of these different types. So a sigma bond is the strongest overlap you can have. So this overlap occurs along the internuclear axis. In other words, both of the orbitals involved in this overlap are going to lie along this line between the two nuclei. For example, the best overlap we can think of would be two s orbitals. I'll use black for the left one, and I'll use red for the right one. Please ignore that horrible picture that I have just drawn. So two s orbitals overlap really well. We can also use two of these px orbitals pointing towards each other. All of their overlap occurs on that internuclear axis. Or if we're overlapping orbitals, we don't have to choose two of the same orbital from each atom. We can choose different orbitals. So maybe I might choose an s orbital on one of the nuclei, and I might choose a px orbital on the other one. This is not an exhaustive list. There are other examples of strong overlaps, but these are the ones that you'll encounter most commonly. Okay, so those strong overlaps overlap on the internuclear axis, and when the overlap is not on the internuclear axis, we get a pi bond. So for a pi bond, the overlap occurs on opposite sides of the internuclear axis. So directly above it and directly below it. And I can give you some examples. So one example where the overlap is on the top and the bottom is if we use these py orbitals that we drew over here. I'm slightly exaggerating these pictures to show where they touch, but I promise that they do. So we can overlap two py orbitals and they touch right here above and right here below. We can also do the pz orbitals, which are difficult to draw. And though you won't see it much in this class, we can also choose d orbitals to form these pi bonds. Because some of the d orbitals are of the same similar shape to a p orbital. So this is an example of a d orbital, and you can see the overlap right here below the bond, below the axis, and right here above the axis. So these are all examples of weak overlap because it's overlap in the wrong spots, not quite in between the atoms. Those are called pi bonds. And sometimes when we put orbitals next to each other that don't overlap, we don't get a bond at all. But it's important to know that that's a thing that happens. Some orbital combinations just aren't good ones. So for example, if we picked p orbitals on two different axes, so one of them on the y-axis and one of them on the z-axis, those are not going to overlap at all. They're nowhere near each other. Or if we picked the px orbital and the py orbital, again, no overlap whatsoever. This orbital has electron density on the internuclear axis, but this one does not. So there's no overlap there. And there are many situations where choosing a d orbital is not helpful. So here's a dxy orbital with the px orbital. Not super helpful. Not a lot of overlap going on there. So these good overlaps are going to result in sigma bonds. These okay overlaps are going to result in pi bonds. And these non-overlaps are not going to result in any bond at all. So sigma and pi bonds are going to come up again later, but for right now, we just need to know that sigma is stronger than pi. And we're also going to need to know which bond we see first. So the sigma bond is always the first bond to be formed because they have the first pick of the best overlap orbitals. So let's add a note about that. First bond to form in a molecule between two atoms is always a sigma bond. It's always the strongest one, because that first bond chooses whichever orbitals it wants, and it picks the ones with the best overlap. If there are more than one bond, if there is more than one bond between two atoms, the rest of those additional bonds are going to be the weaker variety pi bonds. And the rest of them will be pi bonds because the best orbitals were already taken by that sigma bond. We only have 4 orbitals to choose from, and you're not going to be able to get good overlap with all 4 of them with the same atom. So let's make a little table here. It's going to have Lewis theory, valence bond theory, bond length, and bond strength in it. So take a second to copy that down if you need to here. So we're going to describe a single bond, a double bond, and a triple bond, knowing about sigma and pi bonds. So this is the way we draw it when we're drawing a Lewis structure with 1, 2, or 3 lines. In valence bond theory, we know that that single bond, the first one, is always a sigma bond. This is going to be a strong bond holding the 2 atoms together, and the bond length is going to be a long one. When we move to the double bond, the first bond is always going to be a sigma bond, and the rest of them will be pi bonds. So the first bond is a sigma bond, the second bond is a pi bond. It's a little bit weaker. And we know that a double bond is stronger than a single bond because there are 2 bonds holding it together, even if that second bond is slightly weaker than the first one. And as this bond gets stronger, they hold the atoms closer together with that extra strength. And so the bond length actually becomes shorter. So a double bond is slightly shorter than a single bond. And then for a triple bond, as we know, the first bond is always a sigma bond. Those additional bonds are all going to be slightly weaker pi bonds. But when we have 3 bonds together, that bond is going to be even stronger than the other 2 and even shorter. The triple bond is the strongest and the shortest commonly found bond. And so we can use this skill to count how many sigma bonds and how many pi bonds are present in a molecule. So here's an example problem. Count the number of sigma and pi bonds in this large molecule drawn below. I have always found it easier to count the pi bonds first, because when I count pi bonds, I look for double and triple bonds, because I know those are the only places that they're found. So here's a double bond, and I know that a double bond consists of a sigma bond and 1 pi bond, so that's 1. And here's a triple bond in my picture down here. I know that triple bonds consist of 1 sigma and 2 pi bonds. And those are the only place pi bonds are located in the molecule. So that's 1 from the CO, 2, 3 from the carbon-carbon is going to be 3 pi bonds. And now we need to count sigma bond, and there is 1 sigma bond between every pair of molecules. So we just need to count the number of bonds in the molecule. So we've got 1, 2, 3, 4, 5 from this one that we already wrote, 6, 7, we already wrote that one, and 8. It's a pretty straightforward process, but it can be easy to forget to count some of these bonds. So sometimes it's easier to write something or to put a dot with your pencil next to the bonds you have counted to make sure that you don't leave any out. So that is information about orbital distance and orbital orientation. In the next video, we will talk about orbital energy.